Welcome and thank you for stopping by. If you're a first timer, you are looking at automatic magnetic pulser. This circuit specifically works with 220 volt AC. I have another circuit that is pretty much the same as this one, but is designed to work with 120 volt AC. The only difference between these two circuits is in a few components here that I will quickly go over with. So first component is the fan. This component has to work with 220 volt AC. And then low voltage power supply has to work with 220 volt AC to give you 12 volt DC that you will feed later into here and here. Also, main resistor is gonna have to be 80 ohm instead of 50 ohm, and a charging circuit, which is the main change between 110 and 220 volt versions. So if you look at the other one, it has 4 diodes. This one has 2 diodes and only 1 capacitor. I already tested out. It's working pretty good as is described here. It doesn't need another capacitor here because these 2 capacitors will serve the same purpose as another capacitor here for the charging circuit. So this is like completes the charging circuit. And anyway, capacitor bank is the same. It will charge to about 550 volts before low voltage circuit will activate a pulse and discharge it through the thyristor. The last change between 2 circuits is the 500k resistor that's been used into 20 volt AC circuit, and 120 volt AC circuit uses 250k resistor. Everything else is the same. So low voltage circuit pretty much has no change between different voltages, just the resistor here. Alright, you guys, I'm gonna start with let's start with protection circuit. So protection circuit consists of, let me zoom in here, try to zoom in here. You can clearly see it. Alright, 1 second, because it consists here from other components. Your blinking LED here as well. Main component in protection circuit is a transistor. The way it works is it receives 12 volts. It's a PNP transistor, and it completes its line to gets activated through this diode and through this 45k resistor onto the ground. So normally when you give a 12 volt to the circuit, it will if you don't have a voltage here, it will get triggered through this line, and then it will activate the voltage to go into here through the resistor, current limiting resistor, into the blinking LED. By the way, this is not a regular LED. This LED has a small chip built in that makes it blink. So you buy it like that. It's a blinking LED. And when it gets voltage here, it will start blink. So when we have voltage present here, and it's 110 volt AC, it gets limited, current gets limited here, and then the Zener won't allow higher than 13 volt to raise here, and then diode will filter here all the DC out of the AC, and it will charge this capacitor, and it's gonna charge it to about 13 volt, well 12.4 volt. Zener will allow only 13 volt to be here. So as it charges it to 13 volt, it will raise voltage here to higher potential than from this line here. And what will happen is there is not going to be a current flow here between base and emitter, and when there is no current flow, this LED will go off. So this circuit basically monitors for voltage, for AC voltage to come in here. Anytime there is no AC voltage here, this activates, the transistor activates, and the blinking LED will start blink. And let me show you, when we're gonna lose a voltage in two cases: when this relay activates, and that's when thermal protection switch here activates, and it will activate the relay, and relay will open the switch, and as soon as the switch here inside the relay opens, the low voltage will sense that there is no phase present on this hot wire, and it will activate blinking red LED, telling you that thermal protection kicked in. Alright, another part here of this circuit is a power LED. It's pretty basic. It's getting its power from the 12 volt DC through current limiting resistor into the anode, comes out to the cathode, into the ground. So anytime you get 12 volt, this LED will stay on, indicating that you have a 12 volt present into the system. Alright, let's move up, zoom in here. Let's talk about triggering circuit here. Okay, zoom out a little bit. We have a signal from the capacitor bank. Here's the capacitor bank, and we have a signal coming into the low voltage circuit to trigger this 555 chip to activate, to make a pulse. What we have here is a voltage divider. I'm using two resistors, they're 1/4 watt each, because you can use one resistor 500 mega ohm, but needs to be like 1 watt in power. So what's happening here in a trigger circuit, I have put in NPN transistor to assist with triggering and also a 30 volt Zener. At this point here, as soon as we turn the device on and start charging the capacitor bank, voltage will start raising here, and it will get to a point when it will get to about 30 volts. After it gets to 30 volts, the Zener will start allowing anything above 30 volts to pass through, and as it passes through, it raises a current on the base of the NPN transistor, and opens up a transistor through this line onto the ground here. So anytime you have voltage raised to about 550 volt, you will have enough current to activate this transistor and basically complete this line between base and collector. Now this line here is a trigger signal from the 555 chip, and it's connected to the 4K resistor. This resistor is connected to the positive. This is a positive here, 12 volt, and it's constantly keeping the trigger high, so that on the output you will have 0. On the output, sorry, the third is output, you will have 0. So as soon as you lower to 1/3 of the VCC voltage potential here, you will trigger a pulse. The pulse is limited by these two components. We have a circuit 33 capacitor 33 nanofarad with 82K resistor, and these two elements, these two components are setting the 3 millisecond pulse to come out from output anytime you trigger here. But the trick here is that you need to trigger it for less than 3 milliseconds, and the only way to do it is by doing this circuit that triggers it automatically. So anytime voltage raises here, it triggers this transistor triggers it, lowers the value here on a trigger from the chip, and chip triggers and reads the potential from these two components that are setting the duty of the pulse and length of the pulse, which is 3 milliseconds, and it will put it out here from the output into the optocoupler. So this transistor here works as a trigger for 555 chip. Alright, now as soon as we have output pulse from the chip, I have a optocoupler that's getting fed with this pulse. This is a current limiting resistor for optocoupler photo LED diode that's built inside so that it wouldn't burn it. Also, I have 1K6 resistor current limiting resistor for pulse LED. This is a blue LED. I use blue LED, but you can use any LED. This will produce a short pulse, indicating that you have your optocoupler have received the pulse, and you should receive the pulse. Your thyristor should receive the pulse. Now, optocoupler, the other side of the optocoupler is receiving the power through the R3 current limiting resistor. Emitter from this optocoupler is fed into the gate, into the thyristor, and also it has a 10K resistor here. This is a noise limiting resistor, so when there is no signal here, this resistor will keep all the noise to the ground. Also, this capacitor here, I believe it's used for a noise reduction as well. This usually being installed in pretty much all the 555 circuits here. So don't ask me why it's here. I just do it because the circuit calls for it. Alright, let's move on to the discharge circuit, Thyristor, and the air core coil. Here's a little bit more information about coil. It's made out of 14 gauge copper wire, has a 15 layers. Internal diameter here is 1 inch. Outside diameter is 3 inch. Thickness of the coil is 5/8, and total weight of the coil is 400 grams. That's the coils I am using. You can use slightly different coils, and I would like to get some feedback on what other coils work and how well they work. This Thyristor is pretty strong. It can hold, it can discharge in twice lower resistance coil that I have here. But the reason why I'm using this 400 gram of copper here is to increase the amount of time that it takes to heat up, because the less coil you use, less material you use, the quicker it will heat up. So we're let's get to the circuit. We're receiving the signal, pulse signal, and this is a DC pulse, 3 millisecond duration, limited by current with 100 ohm resistor from 12 volt line. So we're getting enough current here to quickly turn on the Thyristor for 3 milliseconds by pulsing into the gate from the optocoupler. The anode from the anode is connected to one side of the coil. The other side of the coil is connected to the positive of the capacitor bank. This is neutral, this is neutral, this is neutral, this is neutral. All of this connections here that indicated with this sign are connected to the neutral. Let me see if I can find some more here. Here on a low voltage side, this must be connected to the, and this must be connected to here. And they're all connected, but they're not connected to the chase's ground. When you have your outlet, you will have one more here. You have a hot, you have neutral, and you also have a ground. So the ground only connects to the chase's body of the case. It does not connect to here. This is the neutral. Okay, neutral, 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 neutral over there, neutral. What else? About the Thyristor, as I said, this can hold at least twice more load than what I have loaded with this coil, and it's capable of putting out more than 14,000 Gauss. More than 14,000 Gauss. Possibly 20,000, maybe 22,000 Gauss. If coil is made out of thicker wire and is not as large. The larger you go, the weaker it's gonna get in size, in weight. So unless you're using thick wire, but still thick wire is gonna offset the distance between your surface of the coil and the farthest edges from the other side of the coil. So it's like, coil is a tricky one. I've been playing with coil for a while, and I'm still learning about it. There is other options, by the way, to use a foil copper or foil aluminum coils, and if somebody can test those out, it would be awesome with this circuit. I would love to get some feedback down below how those coils work. Alright, you guys, thank you for well, let me just go into this circuit here very quick, because that's the only part I missed here. This this is built-in south pole indicator into the coil. What this is a 7 segment or 8 segment, I believe it's 0.75 inch or 0.8 inch LED, red LED indicator. That's what they call them. And you will have like 12 or something legs in it, and you will need to use just the ones to make letter S. Basically, it's a number 5. They're very similar, letter S and number 5. So you will activate first, second, third, and you'll miss couple, and you'll activate just the ones to make a letter S. Alright, and you will put 100 ohm current limiting resistor across it so that it wouldn't be too bright. This would limit its brightness, and also it will increase the current to the relay. This is not necessary, but you can put it here. And this relay, this is a model number of it. Current draw is 25 milliamp, and that's important to use something with this current draw. That's because if you don't use it with this, you're gonna have to adjust it with this resistor here. The current draw for this whole segment should be not more than 5 milliamps. Okay, and make sure it's not more than 5 milliamps, because over time it will start burning them, and you don't want that happen. So limit your current to the 5 milliamps with this 100 ohm resistor. And also in the line, I do have a built-in thermal switch, and this is also a 50 Celsius, just like unit safety thermal switch. This is the coil cell safety thermal switch. When coil gets hot, this senses the temperature and opens the line. As line opens, there is no current flow through the relay, and it will open the line here, and as line opens, it will stop charging through the charging circuit main capacitors. And when capacitors are not charged, the pulser will stop pulsing, because it's not getting its pulse capacitor feedback signal is low, and it's not going to be triggering the pulse. So that's how this protection circuit works. And at the same time, when that happens, this circuit here will sense that there is no hot wire here, there is no 110 AC here, and it will activate this blinking LED telling you that thermal protection here, this went on. Alright, you guys, I think this should, for the most part, give you a general idea how circuits work. And if you have questions, please leave them down below. Also, my website is gonna be down below. You can find more information about that. Thank you for checking out my website, for checking out my videos. I hope you build successfully the circuit and get it to work, and hope that it works. The circuit works very well for you, just like it works for me. I wish you success. If you like this video, don't forget to hit like, subscribe if you haven't done it yet, share it. A lot of people needs to know about this. This is open source, free. I'm giving this away for anyone who's able to build this and put it together. Thank you, and have a great day.